All right, so the last couple of weeks, what we've been talking about is radical expressions, and we've been talking about like square roots, cube root, fourth root, so on and so forth. And we've been doing a lot with like simplifying them, multiplying them, dividing them, adding them, subtracting them, and stuff. But the reason that we can do a lot of the things with them that we were doing, right, is because they actually are exponents. So I know that's kind of a hard thing to kind of wrap your head around, but radical expressions really are radical expressions really are actually exponents. Okay, so you've seen exponents before in terms of integer exponents. So you've seen like 5 squared, you know that's 25. You've seen 5 to the negative 2. Right? Remember that when there's a negative exponent, all it means is that it's basically the reciprocal. So it's 1 over whatever that the negative exponent. Okay. So in this case, it'd be 1 over 25. And you've seen 5 to the 0 power, which is 1. Please remember that anything to the 0 power does equal 1 every time. Okay? And if you're wondering why, I think I proved that. I showed you guys that last year, but there is a reason why that works. Anyway, now when we're going to introduce is rational exponents. And rational exponents means that we've got a fraction exponent. So in this case, if I have some a to the p over r, okay, what this is saying, right, I don't know why I did that. What this is saying is this is the same thing as saying it's the rth root of a to the p, okay? Or it's the rth root of a all to the p. It's the same idea, it's the same thing, okay? So that's kind of what it really means in this. And the reason why this is the same thing is because like if, it doesn't actually have me. Yeah. I'll go black. All right. The reason why this is the same thing, right, is because if I think about this as a to the p times a to the 1 over r, right, this is going to equal a to the p over r. Okay, so that's kind of why they're the same thing, and I don't know why that p's just launched up there so much. Okay. So basically what we're also trying to say is if I think about some like very common ones that we've seen, if I see like a to the 1/2, right, this is the same thing as the square root of a. If I see a to the 1/3, right, this is the same thing as the third root of a, and so on and so forth. Okay, so that the bottom, the denominator in a rational exponent, right, that's the nth root or whatever. So that's the root of it. The top is what what power we're taking that to. Okay. All right. So some examples. All right. If I want to simplify 64 to the 1/2 power, right, this is essentially saying the same thing. Well, this is the square root of 64. And what's the square root of 64? It's 8. Now, normally I would have it, because it's the square root, I would normally say plus or minus 8. All right, but for the sake of what we're doing here today, we're just going to always assume that whatever we're taking of is a positive real number. Okay? So we're always going to assume the positive coming out. Does that make sense? So we're not going to need the absolute values. We're not going to need the plus or minuses. Okay? All right, so now, though, if I look a little bit harder, if I go 16th to the 3/4, okay? So kind of applying our rules, right? So remember that the denominator, this is the root, and the third is this is the exponent. Okay, that's kind of the best way to think about this. Okay? So 16th, 3 to the 4th, right, would be the fourth root of 16th to the 3rd power. Okay. Does that make sense? Okay. So again, so when we simplify this, the first thing we want to do is we want to go, okay, well, what's 16th to the 3rd power? Times 16. Okay. And this is going to equal 4,096. Okay. Now, fourth root of 4,096, that's going to kind of take some guesswork in here. All right, but do I have any fourth roots in here? So a lot of things that we can do the Christmas tree method and look for pairs of 4s and stuff like that. right? Or we can just simply go like type in our calculator, because this is looking a little bit more complicated, right? Another way that you can do this, if you type this in your calculator, you could also write this, and I'm just going to kind of do this in red, because I would prefer you to just simplify this and just tell me what the fourth root of it is, right? But what we can do if we want to type this in our calculator, for example, is we could say, well, this is 4,096 to the 1/4 power. Okay, and that's a lot easier to type into my calculator. Okay. Again, that's just kind of some examples. But again, I want us to try and do this algebraically without having to type it into my calculator. Okay. So another way that we can see this, by the way, and I wanted to point this out, is if I can see the connection between these two. Okay. That means 16th to the 3/4 is the exact same thing as 4,096 to the 1/4. So there's a lot of equivalencies that will occur in these. Okay. So who can tell me what the fourth root of 4,096 is? Anybody? I'm looking at the chat. Actually, where'd the chat go? Oops. What? It's 8. Okay? It's 8. So the fourth root of 4,096 is just simply 8. Okay? Interesting kind of how we get there, right? All right, so now let's look at a third example. Okay? We're going to go 25 to the negative 3/2. Okay? So we're going to kind of take this in steps here a little bit. So again, one of the things that we want to remember is that when we're dealing with these, right, they're exponents. All the same rules apply to exponents. The only difference is that they're fractions. Right? So if I can add fractions, I can subtract fractions, I can multiply, divide, so on and so forth. Okay? So again, since they're still the rules, this is the same thing as going 1 over 25 to the 3/2. Okay? That's what that negative means. Okay? But now from here, this is where I kind of apply my idea of, okay, let's switch this to radical form so I can see it a little bit better. Since that's a 2, all right, this is just simply 1 over the square root of 25 to the 3rd. Now, the reason that I wanted to do this example is I can actually teach you another way of doing this. 25 has a perfect square root, doesn't it? Yeah? Okay. So, another way of thinking about this, right, and this is why that first part was kind of equivalent, is this is the same thing as going, well, that's the square root of 25 cubed. Right? Again, and just kind of highlight, that's applying, right, this part right here, right, saying that it's equivalent. And it is. Right, and the reason kind of why that works, and let me just kind of put this down here, why, right, another way of thinking about this is this could be 1 over the square root of 25 times 25 times 25, right, which is equal to 1 over the square root of 25 times the square root of 25 times the square root of 25, right, which of course equals that. Okay? So, and we all know what the square root of 25 is. It's what? 5. Okay? So this is the same thing as 1 over 5 to the 3rd power. And 5 to the 3rd is 1 over 125. Okay? So that tells us that 25 to the negative 3/2 is equal to 1 over 125. So again, it's not quite so obvious seeing where these guys come from and where these guys go, right? But the important part is realizing that, hey, I can simplify this just by applying my normal rules, okay? So just to kind of, oh shoot, I need to do these two examples first, sorry. My bad. All right, so now we're going to assume that A is negative this time, okay? So we have negative 9 to the 3/2, okay? Applying this, right, we see that, well, this is the same thing as going the square root of negative 9 cubed. What is the problem with this? It's negative, right? So, because it's negative, right, we know that, again, if we kind of rewrite this as the square root of negative 9 cubed, right, this would be the same thing, the square root of negative 9. It would not be a real value, okay? In this case, it would be 3i. Because remember, just kind of a little refresher, square root of negative 1 is I. Okay? So this would be the same thing as 3i cubed. And who remember, so if I is the square root of negative 1, I squared is equal to negative 1. What is I cubed again? Who remembers? What's that? Well, I cubed is a little bit, I mean, it's kind of different, but not really. It is going to be a negative number, but what's I cubed? Does anybody remember? Well, think about it. You've got I, which is square root of negative 1, times I squared, which is negative 1. So it'd just be negative square root of negative 1, which would just simply be negative I. That's okay, Riley. So, if that's the case, I know that I cubed is negative I, and 3 cubed is 27, so this would be negative 27i. Okay, again, I'm seeing some confused faces. Why this works? Remember, this is exponents. This is the same thing, right, as 3 cubed times I cubed. Right? I cubed is negative I. 3 cubed is negative 27. I'm sorry, the positive 27. Apologies. Positive 27. So this is negative I times 27, right? Which equals negative 27i. That make sense?
It does make sense, but I just don't understand why I is negative.
Okay, so y again, kind of going back. So if I think about I cubed, this is the same thing as I times I times I. Okay, which is the same thing as square root of negative 1 times the square root of negative 1 times the square root of negative 1. Okay, well, square root of negative 1, or so if I look at just these two pieces, right, so, but in essence, right, so if I think about square root of negative 1 times the square root of negative 1, if I square those, right, that just becomes negative 1 times square root of negative 1. So another way of thinking about this, well, this is negative 1 times I, negative square root of negative 1 is I, so this is just be negative I. Okay, make sense? So I'm going to have to erase that just because I need to work on the next problem. All right, so now that we have this one, okay, let's try number 5. Okay, I have 27 to the 4th times negative 1 over 12. Again, the same exponent rules still apply. Okay, what happens when we take an exponent to an exponent? What do we do with them? We multiply them. Okay, so this is the same thing as going 4 times, so this is the same thing as 27 to the 4 times negative 1 over 12, right? Which is equal to 27 times negative 4 over 12, which is simplifies to 27 to the negative 1 over 3. Okay? Now applying my rules, this is the same thing as 1 over 27 to the 1/3. Okay? Which is the same thing as 1 over the 3rd root of 27. Okay? Well, what's the 3rd root of 27? What is it? 3. And so see, just kind of applying my rules helps me see these a little bit simpler. Now, again, when you start to recognize this and you start to recognize that these two, this and this are equivalent, I won't eventually need this step. Okay? I can just say, hold 27 to the third is the same thing as third root of 27, so it's just 3. Okay? All right. So now other ways that we can do this is we can go backwards. We can go the other way. So I can write these in exponential form. Okay? So for example, on number 6, if I want to take the third root of x to the 5th, okay? Remember that when I have my form, so x to the p over r, right? My bottom is my root, that's why we use r, and my top is my exponent or power, okay? That's why we used p over r, okay? So, if it's the third root, if I'm writing this as x, my third root, 3 goes in the denominator. And my power, x to the 5th, goes on top, okay? So this would be x to the 5/3, and I'm going to rewrite that just because I wrote it sloppily. X to the 5/3, okay? Now we can do this the same way, okay? So when I'm dealing with something, for example, in number 7, now I've got 2 different variables in here, okay? Which again looks a little bit more complicated, but as long as I apply my exponent rules, it's the same thing. So my root in this case is 1/2, or is 2 because of the power. But if I think about this, what I'm doing is I'm taking a squared b cubed, and I'm taking this whole thing to the 1/2 power. Okay? Because if I'm taking the square root of that whole thing, that's essentially what I'm doing. So that's another perspective of how I could rewrite this. Okay? Instead of having to sit there and do the numbers individually at first, this is going, well, a to the 2 over what. Don't worry about that yet. Take the whole thing and take that to the 1/2 power, and then it becomes a little bit more clear. Okay? So now I've got exponents to an exponent, so powers to power, I multiply. But again, remember, when if I've got 2 parts in here, I've kind of distribute that a little bit. Okay? So this then becomes a to the 2 over 2 times b to the 3 over 2. Well, what's a to the 2 over 2? It's a to the first power, right? Which is just simply a. And then I've got b to the 3 over 2. Okay? And that's this whole thing in exponent form. Okay? You look confused. What's up?
I'm confused. I just don't understand how you guys went through that whole process.
So like I said, first thing we did was we took we used this, and we said, okay, we're going to take that whole thing, because it's the square root of that whole thing, so I can take this entire cluster in here and take that to the 1/2 power, right? If I just kind of imagine that we just call this whole thing x, then the square root of x is x to the 1/2. A little bit of replacement or substitution, okay? And then from there, I apply my exponent rules to just multiply the exponents on the inside. Okay? And we'll review the rules in just a second. And again, number 8 looks a little bit more complicated, right? Again, we're going to apply this the exact same way. Okay? So I'm going to take everything that's in the inside and realize that we're taking all of that to the cube root. Okay? So we're actually taking all of this, a to the 5th, b to the 3rd over c squared. We're taking this to the 1/3 power. Okay? Again, remembering your exponent rules, this is the same thing as going, well, that's a to the 5th, b to the 3rd, to the 1/3 power over c squared to the 1/3 power. Okay? now from here I can multiply my exponents because we're taking exponents to exponents. So this becomes a to the 5/3 times b to the 3/3 over c to the 2/3. Okay? Now it's kind of simplifying this a little bit more. This is the same thing as going a to the 5/3 times b over c to the 2/3. Now most teachers will let you stop there. I ain't gonna do it. Okay? And here's why. You do not have rational exponents in denominators. Okay? And the reason why is because if I just, again, and I'm going to use this in green just to kind of show you, this is the same thing as going the 3rd root of a to the 5th times b over 3rd root of c squared. Okay, so I have a radical in the denominator. Not good. Not good. But the reason why exponent rules, or thinking about these guys as exponents instead of radicals, is when I think about, okay, what am I going to multiply this guy by to rationalize this denominator? Right? I've got 2/3 c's. I want to get 1 whole c. So what would I have to multiply the denominator by to get that? What? I have to multiply it by c to the 1/3. Because when I multiply like bases, right? So c to the 2/3 times c to the 1/3, that's 2/3 plus 1/3, which would give me 3. Right? 3/3, or 1. Okay. But again, remember I have to do to the top, I have to do to the bottom as well. And so now I'm left with a to the 5/3, b, c to the 1/3, all over c. Yes?
So I'm forgetting the rest of the questions, but how come the 5/3 would change into a 6/3? And then
Because it's 5, the base is 5. Or sorry, the base is a.
okay, so c was just
It's just c to the 1/3, yep. Exactly. Again, we're trying to write this in exponential or exponent form. Right? And this is how we would write it in exponent form. Okay? All right. Whew, a lot of information, a lot of questions, I'm sure. Okay? But what I did want to put on here as well, is I did put all of your properties. Okay? These are all your properties of exponents. So a to the 0 is 1. Right? A to the m over n means I subtract the exponents. A to the negative n is 1 over a to the n. And basically all the ones that we kind of just redid in here. But again, we're going to add one more in here. Okay? So if I go, so this is the one that we are adding is the one that we just did. So let's see. Okay, hold on. I got a question. So she asked, why am I multiplying by c to the 1/3 to times c to the 2/3, or instead of c to the 2/3? Okay. So again, I'll use kind of green here to show you. When I multiply these bases, so if I say c to the 2/3, and I multiply it by itself, which is c to the 2/3. Remember, I add the fractions when I'm multiplying like bases. So this is the same thing as c to the 2/3 plus 2/3, which would give me c to the 4/3, which still just gives me a fractional exponent. So I didn't get rid of it at all. The reason that we changed that to 1/3 is c to the 2/3 times c to the 1/3, right? I add 2/3 plus 1/3, which would give me c to the 3/3, which is just equal to c. So that's why we do it that's why we multiply it by 1/3. So another way of thinking about it, right? So let's just say I have, here, I'll erase this. So let's just say I have like c to the, let's go 3/5. In order to make this denominator, in order to make this rational, I would need to multiply it by what? C to the what? 2/5, exactly. Okay, because that'll be c to the 3/5 plus 2/5, which would give me c to the 5/5, which would give me just c. Okay. See that kind of how that all makes sense? Okay. We got to move on though. This class is really short today. All right. So, what I want you, so we're going to do numbers 9 and 10. So we want to write it in exponential form and in simplest radical form. Okay? So we're going to want this in two different forms. So I'll use for exponential form, we'll write it in green. Right? In simplest radical form, we'll write it in blue. Okay? So I'm going to do exponential form first because that'll kind of help me, and it'll actually help us get to simplest radical form. Okay? So when I want to write this in exponential form, so this is square root of 8, which is simply 8 to the 1/2. Okay? 8 to the 1/2. Right? Times the third root of 4, so 4 to the 1/3. Okay? Now, you're probably thinking, oh, well, that's it. That's done, right? Unfortunately not. Remember, we want to kind of make these things like bases. Okay? So, another way that I can rewrite this is 4 times 2 to the 1/2 power times 4 to the 1/3 power. So all I did was rewrite the 8 as 4 times 2. Okay? Which is now, which is the same thing as 4 to the 1/2. Sorry, I wrote that horribly. 4 to the 1/2 times 2 to the 1/2 times 4 to the 1/3. Okay? Recognizing, oh, hey, that means we've got like bases here, so I can add those fractions. So then this becomes, right, 4 to the 1/2 plus 2/3, 1/3, times 2 to the 1/2. Okay? 1/2 plus 2/3 is what? So can you remember our, remember our fraction rules. We want to look for like denominators, which would be 6, right? So we multiply this by 3, we multiply this one by 2's, and so what I'm left with is 3/6 plus 2/6, which should give me 5/6. Okay? So this now becomes 4 to the 5/6 times 2 to the 1/2. And that's an exponential form. Okay? Oh, wait, I'm sorry. There's more. There's more. Okay? Again, so just like we did before, we did 4 times 2. Now we're going to take this one and we're going to go, okay, well, that's 2 times 2 to the 5/6 times 2 to the 1/2. Right? Which can equal 2 to the 5/6 times 2 to the 5/6 times 2 to the 1/2. And converting it back into like denominators, this is the same thing as 2 to the 5/6 times 2 to the 5/6 times 2 to the 3/6, sorry. Which is now going to be 5, 5, and 3, which is going to be 2 to the 13/6, right? I know you guys are probably going, "Oh my goodness," right now. Well, I'm just showing you, like, this is sometimes these are all the steps that kind of go into simplifying some of these guys. Well, 2 to the 13/6 is the same thing as 2 to the, let's see, 2 to the 12/6 times 2 to the 1/6. Which is equal to 2 squared times 2 to the 1/6, which would give me 4 times 2 to the 1/6. Okay. And lots of these with different ones are ways that we can write it in exponential form. But the reason that I did it this way is now when I want to write it in simplest radical form, I've just basically simplified it all. This is the same thing as 4 to the 6√2. Okay. Whew, a lot of work in there, huh? There's lots of different ways that you can go about it. I just did it kind of the very, very, very long way, but you can start recognizing shortcuts in here if you need to, right? We could have instead gone, well, let's rewrite square root of 8 into simplest radical form first and then go backwards. So they kind of work both ways. So if we're doing number 10, okay, again, we're going to try and write this in exponential form. So this is the same thing as 27 to the 3/5 over 9 to the 2/5. Okay. Rewriting the 27, right? Actually, we're going to kind of rewrite them both. Right? And we're going to kind of get them in groups of 3s because we're going to break them all the way down to their base one. So this is the same thing as 3 times 3 times 3 to the 3/5 over 3 times 3 to the 2/5. Right? Which is the same thing as 3 to the 3/5 times 3 to the 3/5 times 3 to the 3/5 all over 3 to the 2/5 times 3 to the 2/5. Adding all of this up together gives me 3 to the 3/6 9/5 over 3 to the 4/5. Okay. Now, remembering kind of our exponent rules again, right? 3 to the 9/5 over 3 to the 4/5. This is the same thing as going 3 to the 9/5 minus 4/5. And what's 9/5 minus 4/5? 5/5, which is just 2. And then in simplest radical form would also be 3. Whew, quite a lot of work. Okay, so I'm going to go ahead and stop the recording.